All right, welcome back to Calculus. Today we are continuing our discussion of concavity. Specifically, we want to talk about what happens when a function changes from concave up to concave down, or vice versa. So like we saw with the first derivative test, we saw that if a function changes from increasing to decreasing at a critical value, then we have found the location of a relative extrema, a local extrema. On the other hand, the first derivative test also told us if we have a change in the function from decreasing to increasing, then we found a local minimum. Okay, so I guess a natural question would be, well, what would happen to a function where we change from concave up to concave down or vice versa? Turns out, and you've heard me mention this word before, it turns out that's called an inflection point. An inflection point is where the curve changes from either concave up to concave down. So this is one difference between the analysis of the first derivative and now the analysis of the second derivative is that there is no, with the first derivative we had to classify either a local minimum or a local maximum, depending on what the change was from increasing to decreasing or vice versa. But with concavity, if there's a change at all from up to down or down to up, what we have found at that point is an inflection point. Now it's very important here with the definition. Here I'll just underline it. Suppose f is a function and continuous at x equals c. Okay, the function has to be continuous at x equals c and change from concave up to concave down or vice versa in order to be an inflection point. Okay, the function has to be defined and continuous. Now, why is that important? Actually, I'll point out in the graph right below. The reason it's important for a function to be continuous at x equals c in order to be an inflection point is that concavity can change in asymptote. So look here at either this region right here around -4 where there's a vertical asymptote, or over here at +4 where there's a vertical asymptote. Notice how the concavity does change at that vertical asymptote. So to the left of -4, the function is concave down. The curvature, the derivative is decreasing. Think about it. There's a slope. There's like a tangent line. There's a tangent line. Those tangent lines are getting steeper from left to right, and the function's decreasing. That means like the slope, like right over here, would be like -1/2 or a fourth. But the slope right there would be like -1. And the slope right there would be like -10. And as you get closer to that asymptote from the left, that slope is getting to be a bigger and bigger negative number. So the slope is decreasing. Therefore, it's concave down. But then if you look to the right of the vertical asymptote at -4, well, okay, at first, the slope is very, very steep. And the function's decreasing. The function's falling from left to right. So like right there, the slope would be like, I don't know, -10 or 15 or 20 or something like that. It's a very steep slope. And the closer you are to the asymptote, the bigger negative number that slope is, like -100, -1,000, -10,000, the closer we are to that asymptote. But as we move away from the asymptote, the slope is still negative, yes, for a little while. But like right here, the slope would be like -1. And like right here, the slope would be like, I don't know, negative 1/3 or 1/4. Then eventually here at -3, the slope is what? 0. So the slope is on the right side of this asymptote is starting off being a massive negative big number. But then as we move away from the asymptote, we're going to be a not quite so big negative number, which means the slope is increasing, i.e. we're concave up. My point there is that the concavity changed at an asymptote. However, x equal -4 is not an inflection point because the function is not defined at x equal -4. The function is not continuous. So the function changes from concave down to concave up at -4, but -4 is not in the domain of the original function. So -4 is not an inflection point. Same thing over here for positive 4. At positive 4, we have another vertical asymptote. And the function changes from concave down over here on the left side. The second derivative is negative, but to the right, the second derivative is positive. So we do have a change from concave down to up. But again, x equal 4 is a vertical asymptote. The function is not continuous at that value. So x equal 4 is not an inflection point. Where are the inflection points here? Well, notice that concavity changes right here. We are concave up in this area. We're concave down to the right of -2. So there was a change from concave up to concave down at -2. So -2 comma f of -2, whatever that y value is, I don't know, like about -2 maybe, is an inflection point. Likewise, notice at -1. At -1, we change from concave down to concave up. And again, these dashed vertical lines, actually, I didn't think about this when I made this graph. So this is a vertical asymptote, clearly, and that's a vertical asymptote, clearly. But in addition, the other vertical lines are not asymptotes. I'm just trying to show you, like, break up the graph where the concavity changes from up or down. So it's just showing different sections of the graph is all those are. Okay, so here, yeah, -1 we change from concave down to concave up. So -1, it looks like comma -1 is an inflection point. Notice here the origin, we have a vertical tangent line. The graph turns vertical for just a moment. And to the left of the origin, the graph is concave up, and to the left of the origin is concave down. So 0, 0, the origin, is an inflection point. All right, and then over here at x equal 1, the graph changes from concave down to concave up. So 1, comma 1 is an inflection point. Okay, then one more of these things here at 2. The graph changes from concave up to concave down at, looks like 2, comma 2. So 2, comma 2 is an inflection point. Because again, at all those inflection points, the graph was continuous. The function was continuous. Okay, so we have inflection points at -2, -1, 0, 1, and 2. And notice there is something curious that happens here. Notice that -1 and +1 and 0 are critical values. So why are they critical values? Because there's a horizontal tangent line right there, and there's a vertical tangent line right there, which means those would all be critical values. But notice they're not relative extrema. So remember we've said this, mention it here and there, but just because you find a critical value does not mean it's going to be automatically a relative or local extrema. So again, here's a great example that there is a horizontal tangent line at -1, 1, and there's a vertical tangent line at 0. So if we were to find the critical values of this function, those 3 values would certainly be critical values. But if we looked at the sign chart, well, notice that f, so here I have f double prime. Okay, these are all the f double prime measurements. But if I talked about f prime, the derivative, notice that the derivative here is positive because the function's increasing, and the derivative is positive on both sides of that critical value. In fact, the derivative is positive right there too, and right there, because the function is increasing. You know what? It's increasing from -3 to +3. Okay, so these 3 circled values are not local extrema because the function doesn't change from increasing to decreasing or vice versa. They are inflection points. Okay, so again, study that graph. There's a lot going on there. And again, like I've said many times, that it's very important to get a really strong graphical intuition as you're in this class. Every test will contain questions that basically are you just looking at a graph and figuring out different aspects, different characteristics of that graph with no calculations involved besides looking at it and figuring out what's a limit. Where's the function continuous? Where's the function concave up? Where is it concave down? Where is it increasing, decreasing? Identify the relative extrema. Identify the critical values. That kind of stuff. Those, having that graphical intuition is very important. Okay. Here, just another little picture just to note that just because we have a situation where it's possible that you have a situation where the second derivatives is undefined or zero, but you don't have an inflection point. Okay, remember that's like where your possible inflection points are. The critical values of the first derivative are where the second derivative is zero or undefined. And notice here's a case in point with this function x to the 2/5, x to the 2/5 power. It kind of looks like I don't know, like how you would draw a bird if you were like in first grade or something like that. Okay, and notice how it certainly has a second derivative. Here's the second derivative. The derivative is certainly zero. If you set that second derivative equal to zero and solve, you get x equals 0 as a solution. So the second derivative is 0 at x equals 0. However, notice that x equals 0 is not an inflection point. Why? Well, because notice to the left of the origin, the second derivative is what? It's concave. It's less than 0, so it's concave down. And then to the right of the origin, also notice that it is concave down. So on both sides of the origin, it's concave down. And that does happen sometimes. Another example might be like x to the 4th power. X to the 4th power, it looks kind of like a parabola that's kind of flattened out at the origin. So it's kind of like parabolic shaped, but it's kind of like, I don't know. Well, that's a bad example, actually. It's a bad drawing. It's kind of like this. It looks like a parabola, except it's more flat at the bottom. Okay? F of x equals x to the 4th. And the same thing will happen there. It turns out, what's the second derivative of x to the 4th? Okay, well, the first derivative is 4x cubed. The second derivative is 12x squared. If you set the second derivative equal to 0 and solve, you get 0 as your only solution. So x equals 0 is like a potential candidate for an inflection point. But notice this function is concave up on both sides of 0. So there is no inflection point here. So that's the point of this bottom example here. On the bottom of page 97 is that it's possible that you get a critical value of the first derivative, and it ends up not being an inflection point. Just like it was possible we got a critical value of the original function, and it's possible that those turned out not to be a relative extrema. Okay, so the same kind of thing can happen with concavity, that you have a location where the concavity is 0 or the second derivative is 0 or undefined, but there is no inflection point there. Okay? All right, let's take a look at a couple examples. So we're going to find the intervals of concavity, so concave up or concave down, 3 examples, and we're also going to identify any inflection points. Okay? First one's not too bad. It's just it's a factored polynomial. I'm not going to bother multiplying that out, and you shouldn't either. I know a lot of students I see on tests, really want to work hard to avoid, say, the product rule, but really, guys, the product rule is way safer than trying to cube this expression, then multiply by x, collect all those like terms and whatnot. I mean, I guess you could use the binomial theorem, but most everybody forgets the binomial theorem. Then you got to multiply by x, and then you have a bunch of terms that you have to take via take the derivative via the product rule. I don't recommend doing that. It's possible as long as you're careful, Just use the product rule, and of course we'll have to use the chain rule too. So let's see, we need to find f prime, and then of course f double prime too. So let's I'll be careful here, and I'll write out the whole quotient, the whole product rule. So we're going to take the derivative of the first function, which is x, times the second function, x minus 4 cubed, plus the derivative with respect to x of x minus 4 cubed. Notice that's composite, times the first function x. Okay. And now let's take those individual derivatives. So of course the derivative of x is just 1, so that gives us x minus 4 cubed times 1 is just x minus 4 cubed. Plus, now we need to take the derivative of this composite function. So let's write down our outside and inside function. Outside function is x cubed. Inside function is x minus 4. So the chain rule says you take the derivative of the outside function. That gives us 3 times something squared. Now the reason I put a blank there is because I know the next step of the chain rule is to insert evaluate at the inside function, which is x minus 4. Then the third step of the chain rule is to multiply by the derivative of the inside function. But what's the derivative of x minus 4? The derivative of x minus 4 is just 1. So we just have to multiply by 1 here, and then by x. So I'll leave off the 1 since that doesn't really affect anything. But then we have to multiply by the x that was already there. Okay, now that's only the first derivative. Remember, we need the second derivative if we're going to look at the intervals of concavity. So now we need to differentiate. Sorry, that's the first derivative. Now we need to differentiate the derivative. So f double prime, well, by the way, let me save a little room. That x goes right there. Let me put that x out front. So let me just fix this really fast. I'm just putting that x in the front. So it was what? There was a square there, and then it was a 3x. I had a 3 there originally, and an x on the back end. I just moved the x out front. It just looks a little better. Okay, now we have two terms we have to differentiate. The first one just requires the chain rule, and in fact, it requires the same inside and outside function that we already wrote down. X minus 4 cubed. That's the same thing we already differentiated. So we know the answer to that. What? It was 3 times something squared, and you put an x minus 4 there, and then we multiply by the derivative of the inside function. So which was 1, of course. But we can leave the 1 off. Okay, so there is, oh, erased a little too much. There's the derivative of that first term. Now the second term requires a product rule, again, because we have 3x times x minus 4 squared. So that's the product of two functions. So, well, let's take the derivative of 3x first. That's the first function. Times the second function. Plus the derivative of the second function, x minus 4 squared, times the first function, which was 3x. Okay, so we have that first part. We're done with that. So 3 times x minus 4 squared plus, well, the derivative of 3x is 3. So 3 times x minus 4 squared. That's kind of weird. We have 2 copies of 3 times x minus 4 squared. Okay. Or sorry, we have two copies of 3 times x minus 4 squared. Plus, okay, now we have another chain rule. This time, though, what's the inside and outside function? The inside function is still x minus 4, but the outside function now is x squared. And so the derivative of the outside function is 2x, but instead of writing x there, we write the inside function, x minus 4, times that 3x that was already there. Okay. What can we do here? Well, let's factor the second derivative, since we know that's going to be in our cards in the next step, because we need set equal to 0 and solve. Let's just go ahead and factor. Notice that each of these terms has a 3, and each of the terms has an x minus 4. So let's factor out a 3 times x minus 4, and then what would be left inside, okay? We factored out, there's 2 copies of x minus 4 here. We factored out 1, and we factored out the 3, so that leaves us with x minus 4. All right, same thing here. We factored out a 3, and we factored out 1 copy of x minus 4, so we're just left with x minus 4. Plus, okay, we factored out a 3 and a copy of x minus 4, so we're left over with a 2 and an x. And so we get 3 times x minus 4. And then what's left over here? We have x and x. That's 2x plus another 2x. That's 4x. Then we have minus 4 minus 4 minus 8. So there's our factored version of the second derivative. Okay, and now we set the second derivative equal to 0 and solve. So solve f double prime equals 0. Well, since we've already done the factoring, that was the harder work, it's pretty easy just to read off our solutions because we have it factored. All right, so the zero factor theorem says that either x minus 4 equals 0 or 4x minus 8 is 0. Well, the first one tells us that x equals 4. That's super easy. And the second one tells us if we add 8 to both sides and then divide by 2, we get what? X equals 2. Okay, so those are the critical values of the first derivative. These are the critical values that basically the possible extrema locations of the first derivative. Okay. Now remember, we should note that we should look for any values for which the second derivative is undefined, but the first is defined. But notice these are all polynomials. The original, the first derivative, and the second derivative are all polynomials which have domain all real numbers and are differentiable for all real numbers. So there's not going to be any possibility of cusps or vertical tangent lines or anything like that. So the only critical values we have are right here. And again, I need to stress when I say critical values, these aren't the same critical values that we talked about when analyzing the first derivative. The first derivative, we have the critical values were critical values of basically the original function. Now we're talking about critical values of the first derivative. These are the like I said a few moments ago. These are the possible locations of extrema, not of the original function, but of the first derivative. Maybe I'll show you what I mean by that with Desmos in just a minute. Okay, but now at the point we have our critical values. This is where we build out our chart. And we look at a number line. And again, the domain of all the functions we're working with is all real numbers. So we plot 2 and we plot 4, and we notice, okay, that gives us 3 intervals for our chart. The top row of our chart is the interval list. Okay, so we have negative infinity to 2. And then we have, what, 2 to 4. And we have 4 to infinity. And now we need to pick test points from each of those intervals. That's our next row. All right, let's see. 0 lives in that interval. That's a nice one to use. I suppose 3 is the only integer between 2 and 4, and I could pick maybe 5 lives in that third interval. And now with the third row, remember we're looking at the sign of f double prime, the sign of the second derivative. Now where is our second derivative? Let's see. Let me box it off so we can go and reference it easily. There is our second derivative. It's the factored version. Okay. So basically, notice that all we have to do, 3 is obviously a positive number. Then we have 2 more factors. So basically, what we have to think about, are those two factors positive or are they negative? If they're both positive or both negative, well, then we have a positive number, because positive times positive is positive, but negative times negative is also positive. But if one is positive and one's negative, then we'll get a negative result. 0 is easy to plug in. If we plug in, again, 0 into our second derivative, we get -4 times -8 times 3. So we have two negative numbers times a positive number gives us a positive result. If we plug in 3, we get 3 minus 4 is -1. So we have 3 times -1, but then 4 times 3 is 12, minus 8 is 4, so we have a positive times a negative times a positive, so that gives us a negative overall result. And then if we plug in a 5, let's see, 3, and then we plug in a 5, we get 5 minus 4 is 1, so 3 times 1 is positive. And then 4 times 5 is 20, minus 8 is 12, so we get 3 positive numbers, and we get a positive result. And so then we just interpret, and we know that where the second derivative was positive, we're concave up. So we're concave up on these two intervals, and we're concave down where the second derivative was negative. Okay, so let's interpret our solution. What does that tell us? First, let's summarize and say, all right, that tells us that we are f is concave down on 2 to 4, and f is concave up on negative infinity to 2 union 4 to infinity. And the last part of this exercise was finding inflection points. So where do we have inflection points? Well, we have inflection points where the function is defined and we have a change from concave up to concave down. Well, the function is defined for all real numbers, so if there's any change from concave up to concave down, or vice versa, then that's the location of a critical value. Sorry, that's the location of an inflection point. So we have two changes. We have a change at 2. We change from concave up to concave down. So 2 comma something is going to be an inflection point. And then we have another change at 4. At x equals 4, there's a change from concave down to concave up. So also 4 comma something is going to be an inflection point. To find the y values, we simply go back to the original function. So we need to plug in a 2 and plug in a 4 into the original function. Okay, so in example A there, okay, if you plug in a 2, well, you get 2 times 2 minus 4 cubed. So 2 minus 4 is -2. -2 cubed is -8. -8 times 2 is what? -16. So that's one of our y values, 2 comma -16. And if we plug a 4 in, oh, that's easy, right? Because if you plug a 4 in, you get 4 times 4 minus 4 cubed. And 4 minus 4 cubed is 0. And 0 times 4 is 0. So the second y value is 0. Okay? Second y value is 0. Let's take a quick glance at Desmos. So our function was f of x equals x times x minus 4 cubed. Okay, so here's our function. Notice it's a 4th degree polynomial, so it's U-shaped. It has a leading coefficient of 1, so it's positive leading coefficient, and it's a 4th degree, so it's basically U-shaped. But it does have a couple twists and turns or so. Notice here that it is concave up, until we get somewhere over here. It's like a section of a parabola until it's opening upward until you get somewhere over here. Then somewhere in here it changes to concave down because then the curvature is kind of bending where it would be opening downward, and then it changes again over here at 4, back to concave up. Now, again, it takes practice to see those subtle changes sometimes. But if you want to like restrict the domain, it might help you. So basically, if we say x is less than 2, that's a part that's concave up. The part that is concave down was between what, 2 and 4. And yeah, you can see that part is concave down. It's like opening downward. And then the part that was concave up again was x is greater than 4. And again, you can see that's like a section of an opening upward parabola. Again, it just takes practice. And if it helps, if you know what the answer is on paper, if you then go to the graph and just imagine what I'm doing here is like covering up half the graph, where you can just see the concave here, the concave up portion, or previously the concave down portion. And by the way, you can verify your answers by, say, plotting f double prime. F double prime there is in purple. Okay? So f double prime, sorry, I changed it, well, purple again. I meant to do that. So f double prime is there in purple dashed. And notice that the second derivative, the purple dashed line, is below the x-axis between 2 and 4, x equals 2 and 4, which is where our original function is concave down. So where the second derivative is below the x-axis, negative, the original function's concave down. Notice the second derivative, the purple dashed curve, is above the x-axis to the left of 2 or to the right of 4, which is exactly what we said where the function's concave up. From negative infinity to 2, that's to the left of 2, or from 4 to positive infinity, that's to the right of 4, that's where the function's concave up, which what we found that to be true was that the second derivative is greater than 0 on those domains. Okay? By the way, what I mentioned a few minutes ago, when I said when we're doing this analysis, we're finding the critical values of the first derivative. Here, let's get rid of the original function. Let's get rid of the second derivative for a sec. Let me do the first derivative. There's the first derivative. When you're doing your second derivative analysis, you're trying to figure out where the derivative is increasing or decreasing. So when I say we're finding the critical values here with the concavity exercise, but the critical values we're finding are not the same critical values we found in the analysis of the first derivative section, is because the critical values we're finding now are we're trying to figure out where the first derivative, so this is the first derivative, not the original function, we're trying to figure out where this first derivative is increasing or decreasing. And notice that the extrema of the first derivative are 2 and 4. The location of those relative extrema are 2 and 4. And that's what we're doing when we set the second derivative equal to 0 and solve. We're finding that 2 and the 4, which are the location of the relative extrema of the first derivative. And so that's why we call them critical values again. I know it's kind of confusing that you have critical values in this situation and critical values in another situation, but we're doing a similar process just using the first derivative now instead of the original function. Okay? All right, let's take a look at the second example. Let's see, it's a exponential. Doesn't look too bad. Let's see what happens. We need to find the second derivative. Let's see here. So let's get ourselves a little room here. G prime is what? Okay, so this is a composite function. So let's see, what's the outside function? The outside function is e to the x. What's the inside function? -3 divided by x. By the way, I'm going to rewrite that as -3 to x to the -1 power, since I would like to avoid using the quotient rule when I take the derivative of the inside function, because remember, if the denominator is a monomial, it's usually, and especially if the numerator is a constant and the bottom is like a plain x or x squared or x cubed, it's super easy just to use the power rule instead of the quotient rule. Although the quotient rule will certainly get you the right answer. All right, let's use the chain rule. Chain rule says you take the derivative of the outside function. Well, lo and behold, the derivative of e to the x is e to the x. Second step of the chain rule says you evaluate at the inside function. Well, the inside function is -3 divided by x. But then we multiply by the derivative of the inside function. So I'm going to do this off to the side to save us a little room down here. What is the derivative of -3x to the -1 power? Okay, well, we're going to use the constant multiple rule and the power rule, which says, okay, we're going to leave the -3 out front. Then we're going to bring the original exponent out front too, and then we're going to multiply by x and then reduce the exponent by 1. So -1 minus 1 is -2. In other words, this derivative is equal to -3 times -1 is +3. And then we have x. Actually, you know what? I'm not going to rewrite it, the negative exponent, because we're about to take the second derivative. So I'm going to leave it as a negative exponent. So it's just 3 times x to the -2. Let me clean that up just slightly, and I'll put the 3 in front of the entire thing, because that's a pretty common thing to do. So let me just do this. I'll put the x to the -2 right there, and I'll put the 3 right there. Since that looks a little better. Okay. Well, now what happens? Well, we have to find the second derivative, and now we have the product of two functions. I guess technically we have the product of 3 functions, but the first function is a constant, so we can use the constant multiple rule to ignore it for the time being, and then use the product rule on the second 2 functions. So we have e to the -3 over x, we have x to the -2 power. So we have 2 functions multiplied together. So we take the derivative of the first function, which, lucky for us, we've already found the derivative, times the second function, plus the derivative of the second function, times the plain first function. Equals, okay, there's that 3 out front. Now we need to find the derivative of e to the -3x. Well, we've already done that. That was the derivative of e to the -3x was exactly the first derivative. So this g prime is the derivative of e to the -3x, because that was the original function. So we can just write down our answer for g prime. That's certainly convenient. So our answer for g prime was 3 e to the -3x over x, times x to the -2. But then we have times this x to the -2 that was already there, plus, okay, what's the derivative of x to the -2? So let's do this off to the side. Derivative of x to the -2 is going to be, well, we bring a -2 out front, x, and then reduce the exponent by 1, so -2 minus 1 is -3. So we get, well, it's plus a negative, so let's just go ahead and change that to a minus 2x to the -3 power, e times the e to the -3 over x that was already there. Okay? So I think that's the second derivative. Hope they haven't made mistakes, cross your fingers. Now we can just simplify it a good bit, I believe, since we're going to have to set equal to 0 and solve here. So let's see. Let's see. I know that I can factor out. Look, both terms have an e to the -3x in them. So I can factor out an e to the -3x. I already have a 3 out front, but now I'm going to have an e to the -3 over x. and then what's left over? So I have a 3 times x to the negative 4 power, calls x squared times x squared, means you add the exponents. So negative 2 plus negative 2 is negative 4. Then I have negative 2x to the negative 3 power. Okay, that looks a lot better. Now, what else? I mean, technically, these are fractions because they're negative exponents. So let's think about combining that into a single fraction. So let me just do some more scratch work off to the side over here. So 3 times x to the negative 4 power is 3 over x to the 4th. Minus 2 times x to the negative 3 power is 2 over x cubed. Okay, right? That's just rules of exponents, properties of exponents. So if we want to get a common denominator, what I could do is multiply this by x over x, which gives me 3 minus 2x over x to the 4th. Okay, so now I can replace that set of parentheses with 3e to the negative 3 over x times 3 minus 2x over x to the 4th, and I think that's our completely simplified derivative. So it started off pretty nasty, but now it's not too bad. Okay, it took a little bit of scratch work off to the side, but that's not too bad. All right, so there's our second derivative. Now we need to find the solutions to g double prime equals 0. And before I do that, I'm going to go ahead and highlight the first derivative so I don't lose it. Okay. And now, what are the solutions to g double prime equals 0? Well, we have 3e to the negative 3 over x times 3 minus 2x over x to the 4th equals 0. Now, I have it in factored form, so I can set those two factors equal to 0 and solve. Well, that gives me either 3e to the negative 3 over x equals 0, or 3 minus 2x over x to the 4th equals 0. Now, we've talked about this on many occasions. For this exponential, well, of course, I guess you could divide both sides by 3, in which case you get e to the negative 3 over x equals 0. But there are no solutions. Okay, think about the graph of that. The graph of that has a horizontal asymptote at the origin. We're looking for x-intercepts. It does not cross the x-axis, so there's no solutions. Also, right here, that is a quotient. It's a rational function set equal to 0. What can we do to solve that? I've said this probably dozens of times now. We can only focus on the numerator set equal to 0, which has a nice solution. What if we say add negative 3 to both sides and then divide by 2? So we get, I guess, x equals 3 halves. X equals 3 halves. Right? If we subtract 3 from both sides and divide by negative 2, gives us a positive result. Okay, so that's a critical value. Now let's also consider the domain of the second derivative. The domain of the second derivative clearly does not include 0 because we have division by 0, x to the 4th. If we plug in 0, you get 0 on the bottom. That's a problem. But notice that 0 is not in the domain of the original function either, because you can't have division by 0 there either. So it looks like there's going to be no cusps or vertical tangent lines because there's no issues with differentiability in respect to there's no points that are in the domain of the original function g that aren't in the domain of the derivative. Clearly 0 is not in the domain of g, but 0 is not in the derivative of g double prime either. Okay, it's a vertical asymptote. Okay, so we have one critical value, but we do need to be careful Because remember, since there's a discontinuity at 0, we have to divide the domain of the function up according to our critical values, or one critical value. But the domain of the function is all real numbers except for 0. So we have to think about, when we're looking at our domain, 0 is already excluded. So we have to have an interval, division here at 0, and then also at 3/2, because again, 0 is not in the domain of any of these functions, of the original function in particular. Okay, so now we can build our chart. Intervals is the first row, so we're going to go from -infinity to 0. Then from 0 to 3/2, that's 1.5. Oh, always having trouble with threes. 3/2, and then we have 3/2 to infinity. Next row is our test points. Oh, let's see. -infinity to 0. I'd use -1. 0 3/2. 1 lives in there. 3/2 to infinity. I'd say 2, since 2 is bigger than 1.5. And now we're looking at the sign of G double prime. I have G double prime here boxed off in red. So let's see. 3e to the -3 over x is always positive, because don't let that -3 in the exponent throw you off. E raised to any power is a positive number. Just because you have a negative exponent does not make your answer negative when you're dealing with exponents. Okay, so 3 times e to the -3 over x, that's always positive. Forget about it. It's always positive. So if we just look at the 3 minus 2x part over x to the 4th, in fact, we can ignore x to the 4th, because we know x to the 4th is always, well, if it's not 0, it's always positive. And we know it's not 0 because 0 is a discontinuity. We're not going to use 0 as a test point. So we know the denominator is always positive. We know that leading term, 3e to the -3 over x, is always positive. So all we have to ask ourselves is 3 minus 2x. Is that positive or negative? Okay, so if you plug in a -1, is 3 minus 2x positive or negative? Well, you get 3 minus 2 times -1 is 5. So it's positive. If you plug in a positive 1, you get what? 3 minus 2, which is positive. And if you plug in a 2, you get 3 minus 2 times 2, so you get a negative. So we have positive, positive, negative here. Are not our usual pattern that alternates. Okay, and then what does that tell us? That tells us that we're concave up where the second derivative is positive, and we're concave down where the second derivative is negative. So let's summarize those results. G is concave up on -infinity to 0, union 0 to 3/2. G is concave down on the last interval, which is 3/2 to infinity. Now, what about inflection points? We have an inflection point if the function is defined at x equals c, and we change from concave up to concave down, or vice versa, at x equals c. So notice the only change from concave up to concave down occurred right here, and that change occurred at 3/2. So we could say, as far as inflection points, that 3/2 comma something is an inflection point. By the way, even if concavity had changed at 0, let's just say for the sake of argument that like the first interval here was concave down, and so there was a change from down to up, 0 would still not be an inflection point because 0 is a discontinuity. It's a vertical asymptote, so it cannot be a inflection point. That's a very common mistake, is for students to say there would be an inflection point in that case at 0, but again, 0 is a vertical asymptote, so cannot be an inflection point. Of course, that's not even what happened. What happened is there was concave up twice in a row, so that here is not even a consideration at all because there was no change from up to down or down to up. It was concave up twice in a row. Okay. To find the y value, we simply go back to the original function and plug in 3/2. So let's see. If we plug into the original function, this would be e to the -3 divided by 3/2. Okay, that's kind of weird, but what do you do when you divide by a fraction? You flip and multiply, right? So this would be e to the -3 times 2/3. Okay, 3's cancel out and give you e to the -2. Now, we usually don't like to write our answers with negative exponents, so if we write without negative exponents, that's 1 over e squared. So the y value is 1 over e squared. So 1 over e squared is our inflection point. All right, let's take a look at the graph. Give me just a moment. So the original function was what? E to the -3 over x. Okay, kind of a weird function. Again, not a function at all that you would have memorized by any stretch. Okay, let's see. It's kind of well, there's the original, so I'll have to adjust this a little bit. So there's the original function. Notice that over here to the left of the origin, yeah, we're concave up. Think about it. The derivative is getting bigger left to right. So like right over here, the function's almost horizontal. So like the derivative is but it's increasing. It's a positive number, but it's a very small positive number. Think like the small fractions, 1/10, 1/9, 1/8. But then like over here, think about it right there. The slope would be about like 1. And then like as you go here, the slope is getting steeper and the function is increasing. So the slope like right here would be 2 maybe. But then like 4, 5, 10. But as you get close to the origin, this function is dramatically shooting off to infinity. It's almost turning vertical. Not ever getting vertical, but almost turning vertical, which means the slope is like 10, 100, 1,000, 10,000. The slope is getting bigger from left to right. And that's what concave up means. The slope is increasing, getting bigger from left to right. Now, to the right of the origin, it's kind of hard to tell. It's a very subtle change. Let me zoom in here. But you have this discontinuity. There's a vertical asymptote, but it's a weird vertical asymptote because there's not the usual behavior on the right-hand side. So to the right of the origin, of course, Desmos is lying here. 0, 0 is not on that function. Desmos is lying. It does that sometimes. But to the right here, let's see. It's very subtle, but you can tell that the function is bending upward from left to right. Again, that means the function is concave up, just like we found. It's concave up until you get to 3/2. And again, if you want to think about this, the function's almost horizontal, but it's barely rising from left to right. So that means the slope is positive, but as it moves to the right, it gets a little bit steeper, which means that's getting to be a bigger positive number for the slope. But then when you get over here to 1.5, 1.5 is about right there, the function starts bending the other way. And what that means is the slope was growing, was getting bigger, but now the function is starting to level off, which means the slope is getting smaller. It's still increasing, it's still positive, but it's getting smaller. Okay, and that's what's happening as the function levels off here to the right. When you level off, that means you're getting close to a 0 slope. It never levels off perfectly, so it never actually gets to 0, but it gets closer and closer and closer to 0. Okay, if you want to verify your answers, for sure, then what you do is plot the second derivative. Here's the second derivative. Notice that the second derivative, the purple dashed function, is above the x-axis when you look to the right of the origin, which means the function's concave up. Now, to the right of the origin, notice that the derivative, the dashed purple, is above the x-axis until you get to 1.5. Therefore, it's concave up from 0 to 1.5. But after 1.5, notice the second derivative is below the x-axis, which means the original function, the green function, is concave down. And again, that change happens right here at 1.5. By the way, we should check to make sure our inflection point is correct. Of course, the x value is 1.5. Is the y value? Now, we set our y value, the exact solution is 1 over e squared. So the question is 1 over e squared equal to, is it approximately equal to a 0.135? I don't know, let's use a calculator. 1 divided by e squared. Yeah, approximately 1.35. So yeah, that is the correct y value there. Okay, but of course we always want exact solutions unless there's some instructions on a test, homework, quiz question that say to round. Okay, so that's example B. Now last one, example C. Okay, a little bit of trig here. I know these are long, but I try to do just a couple examples at a time. I know that this video is one of my longer ones. I'm looking over here at the time, and we're at 56 minutes. But I do want to get 3 examples in here. Of course, you can pause the video and come back if you need to, if it gets a little too long. Okay. Hopefully, we can squeeze this one in here. It shouldn't be too bad. Trig derivatives. You know, it's just sines and cosines. Shouldn't be too big of a deal. So let's see what we can come up with example C. All right, so h prime, we need to find the first derivative and the second derivative. So h prime of x. All right, we have 4 cosine x. So we have 4 times the derivative of cosine x. We know that the derivative of cosine x is negative sine x. That's negative 4 sine x. Plus, okay, we need to take the derivative of sine 2x. Notice that sine 2x is composite. Okay, so the outside function is sine x, the inside function is 2x. So the chain rule says you take the derivative of the outside function, which is cosine x, and then you evaluate at the inside function, so replace x with 2x, and then multiply by the derivative of the inside function, 2. Now, just to make it look a little better, I'm going to put that 2 in front of the cosine, because we know that multiplication of real numbers is commutative. So it doesn't matter if I multiply by 2 in the front or behind. So there's h prime. What about h double prime? Doesn't take much work. Well, we have negative 4 plus the derivative of sine, it's cosine. Plus, okay, well now we have a 2 out front, so that's a constant multiple. We can just write it down and then take the derivative of cosine 2x. So now we have another composite function, so we have to use the chain rule. The inside function is still 2x, but now the outside function is cosine x. Okay, so what's the derivative of the outside function? It's negative sine x. But then we evaluate at the inside function, so we plug in a 2x. 2x. And then we multiply by the derivative of the inside function. The derivative of 2x, of course, is 2. Oh, I just erased too much. That's okay. 2x. So we multiply by 2. Okay. Now, be careful, like right here. Notice I put parentheses here because I notice that a lot of students make mistakes when they have a constant multiple, like we had a 2 there, and then we take the derivative of sine, which gives you a negative out front. A lot of students will make the mistake of saying 2 minus, and then they get to the next line, and they don't remember they're supposed to be multiplying, that they just have subtraction there, and then forget about it. Well, then it messes up the rest of the steps because it is multiplication. It's 2 times that negative sign 2x. So I'm going to clean that up now. The next step, h double prime. So we have that negative 4 cosine x. Okay, we have 2 times negative sign, so we get a negative term, so it's minus. We have 2 times 2, so it's 4 sine 2x. And there's our second derivative. Okay? So now we just need to solve h prime equals 0. Do note that the domain of h is all real numbers because it's just two nice trig functions, two nice cosine and sine functions. I guess I shouldn't say just nice trig functions because, of course, like tangent and cotangent and secant and cosecant have discontinuities all over the place. But sines and cosines are continuous for all real numbers. And notice that h prime only involves sines and cosines and a couple constant multiples. So h double prime is defined for all real numbers as well. So my point there is that there's not going to be any critical values here that are due to differentiability issues. There's no cusps, there's no vertical tangent lines in this function. So all we have to do to find our critical values is solve h double prime equals 0. And before I move along here too much, I'm going to box my second derivative off because we'll need that to come back to when we start evaluating our test points in our table. Okay? I'm not sure why OneNote's telling me I need a password. It's all right. We'll finish the video. All right, so h double prime equals 0. Negative 4 cosine x minus 4 sine 2x equals 0. Now, I do notice there's a weirdness going on here because we have cosine x and sine 2x. We've seen this before, I believe. We need the arguments to be consistent. We either need cosine 2x and sine 2x, or we need cosine x and sine x. And usually the way you fix this is using an identity. But before I do that, I'm going to divide both sides by negative 4 to get rid of those negative 4s, and that'll give me cosine x plus sine 2x equals 0. So now let's resolve that double angle, and let's use the double angle sine identity. The double angle sine identity simply says, okay, cosine x is the same. Sine 2x is simply 2 sine x times cosine x. And now we all have trig functions, sines and cosines, that have the argument x. And at this point, it looks like I should factor. If I factor out a cosine x, since both terms have a cosine, I get 1 plus 2 sine x in parentheses. And now I have this nice factored version of my trig equation, and I can set each factor equal to 0. So the zero factor theorem, we learn it in algebra, of course, but it works in trig and all other domains. Not all other domains, lots of other domains. Or 1 plus 2 sine x equals 0. Okay? So, think about your unit circle here. Here's a nice little space for me to draw a terrible circle for you. Now, hopefully we don't need a unit circle for the cosine x equals 0. Now remember, we're only looking for solutions on 0 to pi. So that means, otherwise, if we didn't do that, then we'd have an infinite number of solutions. So we are only looking for solutions on 0 to 2 pi. So where is cosine 0 between 0 and 2 pi? Well, I think that's going to be true at pi over 2 and 3 pi over 2. Again, because why? The coordinates right there are what? 0, 1, and the coordinates there are 0, negative 1. In other words, the x component is 0. That means the cosine is 0. Okay? So there are two of our critical values. Now we need to solve this second equation. Now, what I'm going to do is I'm going to try to isolate the sine. We've seen this a couple times where we might have solved this exact one. I don't know. If we do that, we're going to subtract 1 from both sides and divide by 2. That gives us sine x equals negative 1/2. So we want to know where sine where the sign, where the y value on our unit circle is equal to -1/2. Okay, so where is sign negative? Sign's the y value. So the y value is negative below the x-axis. So we are looking for an angle over here, I believe, where the sign is going to be 1/2. And over here, I believe. Why? Because the coordinates right there are going to be radical 3/2, comma -1/2. And the coordinates over here are going to be negative radical 3/2, comma -1/2. Now, what are the angle measurements there? Okay, well, I mean, this one over here on the right, I guess you could call it -π/6, but that's not in our domain of interest, 0 to 2 pi. So we need to think about this angle and this angle. Okay, so the first one over there in the quadrant 3, that will be pi plus π/6. I mentioned this before. I don't really bother with memorizing. I don't tell my students, at least, to bother with memorizing every angle on the unit circle. The common ones, at least. Memorize the first quadrant and then use symmetry and use a little bit of geometry and trig to figure out the rest. So we know the straight angle is pi, and we're adding π/6 to it to get to that first answer. So what's pi plus π/6? Pi plus π/6. Well, if you get a common denominator, this would be 6 π/6. So it's 7 π/6 is our solution, our first solution. Okay, so x equals 7 π/6. All right, and then for that last solution, you can think about it this way. Think about 2 pi is the single revolution, but we're subtracting off π/6. Like, we're not going the whole way. This little slice over here is π/6. That is π/6 radians. So if you do 2 pi minus π/6, what do you get? 2 pi minus π/6. Well, if you get a common denominator, you would multiply by 6 over 6. So that's what, 12 π/6 minus 1 π/6 gives you 11 π/6. So if you have all of the angles memorized, that's fine. You would just know immediately it's 11 π/6. But if you don't, you can always use a little bit of symmetry and your knowledge of the first quadrant to solve. So we have, looks like, 4 critical values. Yikes, this is going to make a lot of work for us. But those are all the critical values because we said the second derivative is continuous everywhere, just like the original function's continuous everywhere. All right, now it's time to build out our chart. Okay, I guess let's do this so you can see everything you need to. Oh, let me do that. I need to make this a little lower so in case we have room for all those many intervals. Okay, now be careful here because our domain of interest is 0 to 2 pi. So when we're dividing up the number line, we're starting at 0. Okay, then what's our least critical value? I think it's π/2. There's our first interval. Then we're going from π/2. What's the next one? 7 π/6. Then what's the next one? So we go from 7 π/6. 3 π/2 is the next one. Three π/2. And what's the next one? We have 3 π/2 to 11 π/6. Oh, and then we got to go from 11 π/6 to 2 pi. So I'm going to have just enough room here. 11, oh, not 11 pi yet. 11 π/6 to 2 pi. Just squeezing by there. And that's a lot of intervals. More than I wanted to do with. Now I need to pick test points. All right. Test points. Now, some of these are not going to have convenient test points for us, unfortunately. 0 to 2 pi does, I guess. I mean, you can pick what? Pi over 4, I guess. That works fine. Pi over 2 to 7 pi over 6. Pi, that's a good one in there. 7 pi over 6 to 3 pi over 2. Ooh, there's, I guess, 5 pi over 4 is probably the best one there. 3 pi over 2. Okay, that's another good one. Not a good one. What? 3 pi over 2 to 11 pi over 6. I guess 7 pi over 4 will work. Oh, okay, think about this. 11 pi over 6 to 2 pi. There's nothing on our unit circle there. So what should we do? Ooh, here's what we'll do. We'll just use a calculator this time. Let's look at the decimal approximation for 11 pi over 6. 11 pi over 6 is like 5.75. What's 2 pi? 2 pi is 6.28, right? So we need a number between 5.75 and 6.28. 6 works. We'll have to use our calculator to get it to evaluate. Okay. All right. I got a straight mark. Oh, don't do that. There we go. Okay, test points. Now we need to look at the sign of G double prime. All right, sorry, H double prime. Remember, we don't really care about the exact number. We just care if it's positive or negative. So, boxed off in red there is our second derivative. Pi over 4. Okay. Do I want to just, okay, I need to keep track. I want to keep track of it on the calculator. So I'll talk about it through and then I'll keep track of it on the calculator. So negative 4 times cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So we have negative 4 times, here, I'm just going to use a calculator, times root 2 over 2. Minus 4 times sine, okay, we have 2 times pi over 4, that's pi over 2. So we have what? Pi over 2, negative 4 times sine of pi over 2, that's negative 4 times 1. Okay, so I guess we need to figure out, well, okay, it's a little much to keep track in your head. So I'll just type into a calculator. Sine 2 times pi over 4, you get a negative value. Okay? Negative. What about at pi? Okay, we can probably do this in our head. Because pi is a nice angle. Let's take advantage of the nice angle. What's cosine of pi? Cosine of pi is negative 1. So we have negative 4 times negative 1. That's positive 4. Okay, but then sine of 2 pi is 0. So we get 4 minus 0. So that's positive. Okay, what about 5 pi over 4? All right, so negative 4 times cosine of 5 pi over 4. 5 pi over 4 is over here, this angle right here. The x and the y value are negative root 2 over 2. So 4 times cosine of 5 pi over 4, which is going to be negative 4 times negative root 2 over 2, minus 4 times sine of 2 times 5 pi over 4. I get a negative value. I don't really care what the number is exactly, I just care that it's negative. Okay? What about 7 pi over 4? 7 pi over 4 is this angle right over here. Right there. It has coordinates positive root 2 over 2, comma negative root 2 over 2. So the cosine value is going to be positive. It's negative, but you have negative 4 times positive root 2 over 2. So let's jot that down. Then we have minus 4, but it's times sine of 2 times 7 pi over 4. We get a positive value. Now, if the pattern holds, we should get a negative for the next. Now the negative, we can't really, for the next test value 6, we can't use a unit circle, so we just have to use a calculator. Because again, there wasn't like a nice angle we could use off our unit circle. We could use some identities and get the job done eventually without a calculator, but who cares? Let's just use a calculator. Calculators are here to make the arithmetic go a little faster. Here, I guess the trig a little faster. So 6. Plug in a 6, you get -4 times cosine of 6 minus 4 times sine of 2 times 6, so sine of 12. And you get a negative result, which was expected. Okay, so what does that tell us? Well, our results then are down, concave, down. I was going to say down, up, down, up, down. There's a lot going on there with concavity. Let's summarize our results and then classify our inflection points. So we could say that we are concave, well, let's say H. H is concave down on, okay, that's 0 to pi over 2, union 7 pi over 6 to 3 pi over 2, union 11, always do that, 11 pi over 6 to 2 pi. And then H is concave up on where? Well, it's pi over 2 to 7 pi over 6, union 3 pi over 2 to 11 pi over 6. Okay, now as far as inflection points are concerned, we know that this function is defined for all real numbers. There are no discontinuities. Therefore, any change from concavity up to down or vice versa will be an inflection point. So we have several inflection points here in our interval of interest. Let's see here, inflection points. We're going to have, where's the first change? At pi over 2. So pi over 2 comma something is an inflection point. The second change happens at 7 pi over 6. So 7 pi over 6 comma something. Oh, then we're going to have another change at 3 pi over 2. So 3 pi over 2 comma something. And then there's another change at 11 pi over 6. So 11 pi over 6 comma something, there's going to be 4 inflection points because there's 4 changes. Down to up to down to up, and up to down. 4 changes. And the function is defined at every one of those because the function is defined for all real numbers. Now, to find those y values, we go back to the original function. Now, these might lead to some pretty gnarly y values. I'm not sure. I don't remember. Let's see what happens. Pi over 2. First, I'm going to jot down the original function. 4 cosine x plus 2 sine x. 4 cosine x plus plus sine 2x. Sine 2x. Okay. Pi over 2 is easy. We plug pi over 2 in. What's cosine of pi over 2? 0. So we get 4 times 0. I'll jot down scratch work. 4 times 0 plus, okay, we plug in pi over 2. You get pi over 2 times 2 is pi. So it's 0. Plus sine of pi is 0. So you get a y value of 0. I wasn't expecting that. Okay. If you plug in 7 pi over 6, okay, you have 4 times cosine of 7 pi over 6. The cosine value, ooh, this is not going to be nice, is negative, so I'll put a negative out front, root 3 over 2 plus sine of 2x. So sine of 2x, that's 7 pi over 3, or 7 pi over 3. Is 7 pi over 3, is that, that's not one of our nice angles, but is it coterminal? Sine of 7 pi over 3. Is that coterminal to anything nice? Well, let's see. 7 over 3 minus 2 Yeah, it's pi over 3. It's coterminal to pi over 3. So 7 pi over 3, if you subtract off 2 pi, it's coterminal to pi over 3. So this we could say is the same thing as pi over 3. Okay, so what's sine of pi over 3? Well, the sine value is root 3 over 2. Mirrored in a circle. So plus root 3 over 2. Well, at least we have a common denominator already. We can just combine. So let's see. We have to give it a little more space over here with our y value. So the common denominator is 2, and we have, actually, it's not that bad. We have negative 4 square roots of 3 plus 1 square root of 3, so that's what, negative 3 square roots of 3? We'll check ourselves. I'm going a little fast here, so hopefully I don't make an error. All right, what about if you plug in root 3, sorry, not root 3. What if you plug in, oh, and I just erased way too much. What if you plug in 3 pi over 2? Okay, if you plug in 3 pi over 2, cosine of 3 pi over 2, that's this angle right here. Cosine of 3 pi over 2 is 0. So the first term is 0. Plus sine, okay, sine of 3 pi over 2, that you multiply by 2, because there's a double angle. So you get 3 pi over 2 times 2 is sine of 3 pi. Well, that's coterminal to pi, and sine of pi is 0. So again, we have a y value of 0. That's nice. And now we have another harder one, 11 pi over 6. So let's see. What's cosine? We have 4 times cosine of 11 pi over 6. Now that's the cosine value of 11 pi over 6. That's right here. Here's 11 pi over 6. That angle right there. Okay. So that's root 3 over 2 is the cosine value. Plus, okay, sine of 2 times 11 pi over 6. Okay, so we have what, 11 over 6 times 2. Now, so that's, if we subtract off, we get a 5 pi over 3 is our coterminal angle. If I did that right, let me double check that. So you have, we're plugging in 11 pi over 6. So 11 over 6, but we're multiplying by 2 because it's a double angle. Okay, then we're going to subtract off 2 pi because we need to get back into a, yeah, it's 5 pi over 3. Okay, so 5 pi over 3, so what's the cosine, no, the sine value of 5 pi over 3? Well, it's negative root 3 over 2. Okay, so, oh, notice that, okay, we have a little symmetry here. It's positive root 3 over 2. Sorry, positive root 3, sorry, can't talk. 3 root 3 over 2. Yikes. All right, let's check this last one. We're almost done. Almost done here. Just want to check to make sure our work is good. So what's the original function? It was 4 cosine x plus sine 2x. And we are only interested between 0 less than equal to x less than equal to 2 pi. All right, so there's our kind of a weird function. Okay, it's kind of hard to tell about concavity there. I mean, it's clearly concave down to start with. And then, yeah, that's a definite change at pi over 2. Here, if we just kind of, say x is less than pi over 2. Oh, let's see. X is less than pi over 2. Yeah. Oh, 0 pi over 2. Yeah, that's definitely concave down, which what we found to be true. It gets kind of weird though. It gets kind of weird to the right though. So let's see here. 2 pi. You know, then it's concave up for a little while. Then there's like this little bend over here. So it's definitely concave up here, and then there's a little bend. So where's that little bend happen? It looks like it's 7 pi over 6 is where that next change happens. So there's somewhere over here, which is 7 pi over 6. So let's say x equals 7 pi over 6. So yeah, like right there, there's a change. It's 7 pi over 6, and then it's concave down. You can tell it's like bending down over this little region. But then at 3 pi over 2, yeah, okay, at 3 pi over 2, it starts kind of bending upwards again. Okay, at 3 pi over 2, it starts bending upwards. And then over here at 11 pi over 6, somewhere like right in there, it starts bending downwards again. Let me put a vertical line at 11 pi over 6. Okay, so notice here these vertical. I'll put a vertical line where everywhere where the concavity changes. So we had x equals pi over 2. I'll make them all red. There's a lot of changes in this one. And then x equals 3 pi over 2. So in every one of these red lines, the concavity changes. And so sometimes it's good to when you're doing this kind of thing to add those lines so you can really visually make a distinction between where there's different sections of concavity. So here, we're clearly concave down. That's easy to see. Then over here, we're concave up. That's easy to see too. Big, nice, distinct sections. But then during this little section right here, it's really subtle, but we are concave down because we're kind of bending. The derivative is getting smaller, not as steep is a good way to think about that. But then in this section right here, the bend goes the other way. We're bending upward, which means the derivative is getting bigger because the graph is getting steeper. And then over here in the last little section, the bend is going down again. It's really subtle, but the graph is getting less steep is a way to think about that. Okay? So there was a lot with that one. Lots of changes in concavity. And then of course, let's double check our inflection points. So of course, here let's turn these off. We had a pi over 2 comma 0, so check, that's good. 3 pi over 2, 0, check, that's good. Now let's check the y values of 7 pi over 6. Let's just plot these points. 7 pi over 6 and see if they land on the graph. Comma -3 square root of 3 divided by 2. Yep, that's on the graph, so that's good. And then the other one, here we can copy that because it's kind of similar, was 11 pi over 6, and its y value was positive. Yeah, so our y values were correct because they land right on the graph. Okay? There's the decimal approximations. But again, we don't want to use decimal approximations unless instructions explicitly say to do so. Okay, so I know this video was a heavy lift. If you're here at the end, I applaud you for sticking around. Of course, if you on these videos, if they get long, if you need to take a break, please take a break. I try to keep them much shorter than this, but these 3 examples were pretty intense. So, just to summarize real quick, we find intervals of concavity by looking at the second derivative. We find where the second derivative is either 0 or perhaps undefined. But that, again, has to be in the domain of the original function. And then we build out a chart using the sign of the second derivative, and that will allow us to identify where the function's concave up or concave down, and then we can look for switches in concavity from up to down. If that switch happens at a continuous point, and you go from up to down or vice versa, you found what we call an inflection point. Okay? And that's where the derivative changes from either increasing to the second derivative changes from either increasing, that's where the second derivative changes from positive to negative, which is where the derivative changes from increasing to decreasing or vice versa. Okay? All right, if you have any questions, always feel free to reach out. I'll catch you in the next video. Thanks for sticking around.